So I thought, hey, look, if we have a complexity function that is allowed to take on the value of 0, keep in mind this is a very convenient definition for us. It doesn't necessarily have to be that way, but we'll talk more about that at some point. But what I want to do is I want to see if I give you a function. So if I give you a function f, and it spits out 0 always, so is that big O of 1? So does 0 belong to this set of complexity functions? Does it belong to big O of 1? So let's prove that using the definition of big O, if that's the case. So let's prove it together using the definition. Now remember, the definition says that there exist these two constants. Remember, this is a positive real number. This is a positive integer. We have to find these two constants such that for all n greater or equal to n0, let me just add that in right here. It has to be that this inequality is satisfied. So let's prove this together. And this is a really easy one, okay? You can easily pick up the pattern of this proof and use it in all sorts of different places. So to prove the claim, so I always like to make sure I start off with a little game plan so that the reader knows what we're doing. To prove the claim, we compute constants C, which is a positive real number. That's what the Blackboard R is with the plus. And n0, which is a positive integer, so that 0 is less than or equal to C times 1 for all n greater or equal to n0, right? So that's what the definition would be if we applied it. But notice that I want to get it so I pick up these two constants. So I got to find two constants. I want to pick them up. And I want to argue that these ones will work so that when I pick up and use the definition, so I'm just going to apply the definition of big O, it clears. So now this one's really easy, right? So let's simplify what we got right here. 0 is less than or equal to C times 1. So notice that C has to be a positive real number, right? So what does that mean then? Can it ever be that these are equal to each other? No, right? It has to be that there's a strict inequality here. But to make this easier, because remember, all we have to do is present C and n0, right? But we have to check that they work by presenting an argument. So I'm going to select C is equal to 1. Let's go C is 1. So when I put C is equal to 1 in here, notice that this becomes just 1 times 1, which is 1. Then 0 is less than 1, right? Which is a subset of this statement, right? For all n greater or equal to 1, right? That's what it says. But that means that I'm satisfying the inequality always. So I'm just going to say by selecting, sorry, I was getting a little ahead of myself. By selecting n0 is equal to 1, we satisfy the definition of big O. And 0 has to be in big O of 1. And that concludes the proof. This one's a very easy one to prove, right? It's nothing too scary about this one. Remember the game plan. You find C, you find n0. It doesn't matter what order you do this. The recommendation I have for you when it comes to proving claims like this is you pick one of the constants, then you try to check the other one. So by formulating or deriving it. Sometimes it'll be a case where you can just choose both of them and then you check them, or you derive something by doing some algebra on the inequality, presuming the given domain of the numbers that we're working with, and then you get C and n0 at the end. There's several ways you can go about it. This is just one fairly standard way. But yeah, no, so now we know that 0 is in big O of 1. Pretty interesting stuff, right? So that brings me to an interesting question. So this is more of an academic question. That's the easiest way I could describe this question to you. It's more of an academic question because this, so now that I've told you what the definition of big O is, I've told you what we're considering complexity functions for our discussion. Remember, they could be, it's where the function takes in as input positive integer starting at 1, 2, 3, but you're also allowed, if you need more convenience, you can always make it so it starts at 0, but the output always is non-negative, meaning it's going to be negative. Sorry, no, it's always going to be 0, right? That's what non-negative means. It's not going to be negative. It means that it's going to be allowed to be 0 or greater. It can be fractional numbers. That's the whole point. It's allowed to be a real number. Now, in a lot of algorithm analysis, you don't need to go that far. Usually, just having a positive integer that gets outputted from the function is sufficient. That's typical for algorithm analysis. But from a lot of the models at play, very often you'll have it where the constants themselves appear in the running time depending on the analysis. But that's a whole other side. So now I'm going to ask you an interesting question as a consequence of this. Is big O of 0 equal to big O of 1? Now I mean this in the most literal sense. This is an actual equal sign. So what I'm saying is, if I gave you big O of 0 and I give you big O of 1, are they actually the same? So are these the same? So what do I mean by that? So let's take the idea we have over here. So the first thing I need to show you is, remember that 0, and I must stress, you can take and pick up that proof that we just did over there. You can easily adapt it to show that 0 is in big O of 0. So you can do that. It's totally, if you use our definition, you're allowed to do this. But the question is, if I check what 1 is, so if I look for the function that outputs 1, is it inside of here or is it outside of there? That's the question we're going to address now. Like I said, it's a fairly academic question. So let's get into this. So the first thing is how do you know this? So remember that you think of these as buckets. So what my claim is what we're going to see here is whether 1 is in this bucket or there's another bucket out here that it doesn't, that it's sitting in. Because remember, that's how we talked about big O. It's going to be where the asymptotic orders of them nest into each other like that for the most part. So for what we're talking about. So, but we don't even need to go that far. We don't know whether it is going to be that these are in the same bucket or that these belong to two different buckets. But you're going to see that it's going to be more that it relates more like this. Because remember, what we established earlier is that 0 is big O of 1. And this is 1 right here, right? So naturally, a question is there a function that is not in here that's in here? So let's pick the easiest thing I can think of. So what I'm thinking, maybe we'll consider the function. We'll consider a function for which it outputs 1 always. It's just a constant function. So you might ask, Dan, how do we know? Like first, how do we prove that a function isn't big O of another function? So do you remember our definition? Remember, our definition says that there exists a positive real constant c, a positive integer n0, such that this inequality holds for all n greater or equal to n0. Remember, in the game plan that we had, we would, what did we do? We find c and n0, and then we check to make sure that that works always. But we need to have an argument to do that. But, well, how does it work if I wanted to show you that you can't do this? What we would call the logical negation of this statement. So you can think of this like a game. So in that game, I have to pick up a c and an n0, and I have to show them to you and see if they work, right? Well, if somebody wanted to refute your claim, what would they do? Well, what would they do? Like to say that, oh, this function is not big O of that. What would they need to do? Well, think about it. If these two exist, these pairs of constants exist, and I can check it, we're good. So if I want to say that that f is not big O, then what does that mean? It means that you cannot find any pairs like this. So let me phrase this a little bit more carefully for you. So f is not big O of g if and only if for all c, remember it's a positive integer, this stuff doesn't change, right? These are just what I'm working with. And n0, which is a positive integer. So let's think about this carefully. So remember, it has to be that no matter which pairs I pick, do you remember when I first introduced big O to you, I plotted out two functions. I told you that there was eventually a point for which one of the functions dominated the other one. So how would I pop a hole in that bubble? So how would I show somebody that that doesn't work? Well, here's the thing. If I were to presume that if I picked up from an arbitrary bucket, suppose that there's a bucket of C's and N0s I could pick out, and I put them together. If somebody tells me those work, how can I show that I can refute that? Well, it's really not that bad. Well, remember, the whole thing was that one of the functions dominates the other by some constant multiple after some point n0. So all I have to do is show that if you give me that n0 and you give me that constant c, that I can find a value of n that happens after that, where that domination doesn't happen anymore, where the one function no longer dominates. At one point, any one point will suffice. So the game plan's a little different here, just a little. So if and only if for all c and n0, there exists n, which has to be greater or equal to n0, so this is some positive integer that is greater or equal to n0, such that what? So what did it mean to make it so that one of the functions goes a little higher than the other one by that constant multiple? It means that the inequality is false, right? It got refuted for that value of n. So this is what we would call the negation of the big O definition. So this is one standard way you can prove that a function is not big O of another function. So this is one way. Another way you could reformulate this is by using what we call proof by contradiction. There's other ways too, but we're going to use this one for this little exercise we're going to play around with. So we're going to consider this function here. So my claim, the claim is that 1 is not big O of 0. If that's the case, then it has to be the case that 1's sitting outside of big O of 0. So let's prove this together. So now that we have a logical framework for how we can go about this together, let's see what we can do. Now remember, now the game plan has changed. Now somebody's going to give me, as an adversary, they're going to give me C and N0. They're going to challenge me. They're going to say, hey, look, I got C and N0. What's my job? I have to give you a value of n such that it satisfies this property. That's the game plan. So I have to find n. So I don't have choice over C and N0 anymore. Somebody else does. But my argument has to work regardless of what C and N0 are. So you're going to see that the way this argument's going to work is that I'm going to have to be careful when it comes to this. So let C and N0 be arbitrarily chosen and fixed. So now remember the game plan? We're going to just say what the game plan is. So we find n greater or equal to n0, so that this is gonna be one of those proofs where as soon as you write it out, it's just like, oh yeah, that's kind of easy. Right? So that 1 is greater than c times 0. So here we go. Well, what's c times 0, everybody? It's 0, right? So let's write that. Well, c times 0 is equal to 0. So 1 is greater than 0 regardless of c and n0, right? It doesn't matter what c and n0 are. The point is now I have to pick n0. Sorry, pick n. Remember, you don't want to get those two mixed up. You want to pick n that's greater or equal to n0. So I'm just going to pick n0 to be, sorry, I'm going to pick n. I want to walk you through this thinking process, okay? So I need n to be greater or equal to n0. So what can I pick for n? I'm just going to pick n0. So I'm sort of trying to give you a little bit of a hint here or there. So choose n is equal to n0. And the inequality is satisfied. Now I'm going to pick up my negation of the big O definition and just invoke that. Therefore, by the definition of big O's negation, or what I would personally write if I was not doing this right now on the board, I would say by the negation of the definition of big O. So by the definition of big O's negation, 1 is not big O of 0. So the answer to this question is no. They're not the same sets of complexity functions. What it says is that 1 is sitting outside of big O of 0. And now, you might ask, Dan, why would we care about that? Well, this also gives you an indication that 0 is a little different than just any constant, right? It's just a little different, because what you can do is you could actually pick up and prove using the definition of the big O that, say, for example, big O of 1 is equal to big O of 2. Likewise, you can prove that if I give you two positive real constants, I can show you that big O of C1 is equal to big O of C2. Likewise, this simply means that I can compare, I can say, hey, look, any constant function, that long as it ain't 0, I can say that this set is equal to this set. This is equal to any constant d. So if this d is greater than 0 is a constant, all of these sets of complexity functions are exactly the same one. So when somebody asks you, so a very common question that does come up is when people first see big O of 1, they say, why is it 1 as opposed to like big O of like 5 or something? It's because all of these are the exact same set, all of these. So it's easy enough to just call it big O of 1. That's a nice elegant way of classifying it. So if we're ever talking in terms of big O about, say if we're talking about a running time that takes constant time, normally it's expressed with big O of 1. If it's specifically constant, then you could say something else too. But the point I'm getting at is that big O of 0 is a little different. That's the main message here. So that's why it's one of these edge cases you have to be careful about. So you can say that 0 is big O of 1, but actually you can't say that they're equal. What you can say is that big O of 0 is a subset. So a fancy way of writing this is using this kind of rounded inequality here. Say, you can say that big O of 0 is a subset of big O of 1.